I finally have some time, so I decided to make a video on the topic of how to make a satellite. It isn't difficult. We will see that in a minute. Right. Before I continue, disclaimer. CIA, NSA, FBI, military, the US police and whatever. If you do not like my video, if there is a legal reason for this video to not exist in the internet, then please let me know before you send a SWAT team knocking on my door. Oh wait, SWAT teams don't knock on the doors. You know what I mean. Nevertheless, we'll be making a satellite. What does a satellite mean in the first place? A satellite is an object which has been deliberately placed in an orbit. The orbit does not necessarily have to be a closed curve around a larger object. It can as well be a curve or a segment of a curve which intersects the surface of the larger object. Which means if I drop a sandbox from a church tower whose path eventually intersects the Earth's surface, i.e. the sandbag falls on the ground, it's still describing an orbit. The motion of the sandbag in that orbit is principally governed by the gravity of the Earth. If you push the sandbag a little bit forward before you drop it, then you will have a parabola describing its flight path, which is also an orbit driven out of the gravity of the Earth. So we'll be making a satellite which we will not take to space. Of course not, I do not have the resources or the equipment to build such a satellite. I'm too poor for that. We'll be making a satellite which you can perhaps lift with a sounding rocket or with a balloon and then release it at some point in the stratosphere, and it will fall along an orbit which will eventually intersect the Earth's surface. In fact, if you look at it in this way, then the satellites which are in a stable orbit, they're also falling towards the Earth, but their fall is perpetual. My satellite will fall, and its fall will eventually find a conclusion. So, what do we need in order to build a satellite? Of course, building material. My first building material are to be scavenged from household things. So for example, I can use this cola can. In fact, making a satellite or making a probe out of a cola can is a rather popular thing to do. It is called a CanSat. You can take a look in the Caltech webpage or in the description of the video for more information on this. Nevertheless, I decided to start my satellite building using not those cola cans, but using this stuff. So this is a drink bottle. It contained apple juice, and the bottle has a square profile, so you can cut out a cube out of this. A cube eventually has some more interesting aspects to form the outer skin of a probe. If you're trying to make some eye-candy pictures from a satellite, or if you want to make a satellite which just sends a couple of pings from the space, then these things wouldn't make any difference. But nevertheless, I find them really interesting, so I'd like to speak on them. A cube, for example, if you cut it out properly, then all its three principal axes of rotation are roughly equal. Of course, there will be some unequal distribution of mass inside the satellite, but I'm ignoring that in the first place. And if you have three almost equal axes of rotation, then it is much more easier to describe the cube's tumbling during free fall. Now, of course, easier is also a matter of personal taste, and while I will be uploading this video using a laptop, there are certain parts of the mathematics, there are certain expressions in the mathematics which I still like to do on a pen and paper. And when I'm doing it on a pen and paper, then the description of a cube's rotation is something which I really like. In a sense, I prefer to see that above the description of something else. So I'll be using this. Speaking of it, a cube, while operating inside the atmosphere, is probably not the best thing. No, I'm not talking about the aerodynamics. I'm talking about a following or marking grid cells. So if you have an atmosphere which you eventually would like to describe using techniques of finite element analysis, then you have to split the atmosphere in small grids. And if you want a probe which naturally fits into those grids, then you might want a cube Or even better choice is a tetrahedron. Now, a tetrahedron is the topic of my thesis. I'll be talking about that when I finish writing my thesis. Nevertheless, we start with the cube. So, we first have to measure out how big the cube is. I'll be using my slide calipers, a digital slide calipers. The problem is I bought the slide calipers from eBay China, and it isn't the best thing that you can use. As it can be seen, it makes a lot of mistakes. The strain gauge inside the device flips around, so when you're moving this, the strain gauge inside this just keeps on flipping left and right and gives you an error of about 5 to 10 millimeters, which is a large error if you ask me. So nevertheless, let's zero it. The zero reading right now is flipping between 0 and 0.01, so we'll be zeroing this. The yellow button. Yeah, I know, eventually I'll have to buy a better slide calipers, but right now I'm too poor. So, let's measure this out. Box and slide calipers. No, I'm in a bottle and slide calipers. I'll be opening the slide calipers very, very slowly so that the strain gauge doesn't have the chance to flip around. Wait, I'd like to remove the paper around it first in order to avoid mistakes in the measurement. So I take my knife and simply cut it. Right, come on. So here is the adhesive part, which I have to scratch off, in a sense, with the knife. And, well, I don't want to cut my fingers, because every time I'm using the knife, sooner or later I end up with small wound in my fingers. So, there we go. The cover has been removed. And we'll be opening this very, very slowly. Right, I've got a mistake. It says 56.25 while it is actually 60, so I have to zero it again. So you see, it shows in the zero position that the measurement is minus 5.09, which means that the strain gauge has been flipping around. This is what I mean by I'm extremely disturbed by this device. Well, I'll buy a better device when I have some more money. There, zero. So let's go again. This is more plausible, a little bit more. Right, 70.58, it looks good. Right, we've got 70.58, I like this. This can describe my outer dimensions. So the width is 7.58. I'll be measuring the breadth, the depth I mean, 7.58 as well. Well, it's flipping between 7.58 and 7.60. So I'll be marking 2 points on the length so that it's becomes almost the same. No, we'll not be marking, we'll be cutting out as large as we can cut it out. Right, we'll close it. We'll zero it. And we'll be taking our knife again. But before that, I need a drink. Not bad, not bad. So, again the knife. I mark it less. No, this is too soft. I need a bigger knife. This one will do. A better choice. So, mark it less. Mark it less. There, it's been marked. It cannot be seen, but there is a scratch, there is a cut through. And this cut is what I'll be following. Well, if you look very carefully, then you'll see that the cut has gone to the wrong direction, but that's not a problem. We'll be smoothing it out in a minute. Right, so let's cut it. In order to cut that, maybe I'll drop the camera a little bit so that the cut can be seen more clearly. There we go. And now cut it through. 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 And what do the French say? Et voila. Yeah. So we have to do the same thing on the other side as well. So we'll be cutting it there. Come on, there. Come on, come on, come on. Don't make daddy sad. Right, this one is slightly botched. It can be seen very clearly because of the slight curvature of the profile caused my hand to shake a little bit. Well, I know that's not the best thing to say when you're making a satellite, nevertheless it happened. So I'll have to smooth it out. How do I smooth it out? I'll take my scissors. And cut off this unnecessary little plastic thing. The other good thing about having a cubic, or in this case a parallelopoid profile, a parallelopoid outer skin, is that you have a relatively large freedom of where to place your hinges. When you want to cut out a panel on one side and want this panel to open and close, you will need hinges. So you have a relatively larger freedom to use a hinge on a parallelopoid than you would have, for example, on a cylinder, or well, the relative amount of freedom on a regular tetrahedral pyramid is almost the same. Nevertheless, we've got this. This looks good. This will be our satellite. We have already mentioned that this satellite will not go to space, so right now I'm not that worried about radiation behavior or safety against radiation. Nevertheless, we have to fill in the components inside it. In order to fill in the components, I will be using different boards, which will be different cards. I'll be soldering the boards with electronic components on them a little bit later, and right now we talk about the structure itself. The boards, yes, of course, the boards or the cards. They will have to fit inside the satellite. So for example, for that purpose I have this stuff. I take one out, and this does not quite fit in the satellite, so I have to cut one out to fit snuggly inside it. You can see that the fit will not really be that snuggy, in the sense there will be some space on both sides. I can even leave some spaces on both sides and on the top and the bottom, and that will give me ample space to fit in my wear routing. Wear routing is a really big problem for a proper space application, which also requires you to collect useful data. So, as I already said, if you're looking for eye candy pictures, you will not need all these problems to be meticulously solved. But if you're trying to collect data which has scientific value, then you will have to solve this. So, let us cut it out. How many millimeters there were? 70.68 one thing. So I'll be cutting out 7.68 millimeters out of that. Let's see if I get that. 70.68 almost, right? So a little bit more. There we go. Well, this is now not completely 70, it is 69.9 something. Well, let's say 70 point something millimeters. I'll be taking that. It has to fit in, not snuggly, but leave some space on top and on the bottom. So let us see how big this is in the wide side. In the wide side, it is about 50.50 millimeter wide. In the long side, it is much larger than 50.50 millimeter long. So I'll be cutting out 50.50 millimeters, and I mark that out. This is this one here. Right, so I take the bigger knife and use that as a guide. So once again, there we go. Oh no, we close this, we take the bigger knife, we take the slide calipers itself and use that as a bigger knife, as a guide to drive the knife, and mark out and cut out a groove through the little holes inside it. Right, the groove has been cut. The groove has been cut. It is not very clean, but it's the groove, so I'll be using this to break the board in two. And voila, it has been broken. So there's a little bit of problem at this side because the groove was not really clear there. So I'll be again using my scissors to chop off unnecessary parts. Voila. Right, I'm not a Frenchman, so I should refrain myself from using French expressions. So, we got our circuit board. It doesn't have any components, but this will serve as the basis of our card to do one particular job inside the satellite. And we can see that the card goes inside the satellite and it leaves ample space on all four sides. So this will serve as the basis, this will serve as the places for our wire routing. So, this will not be the only board. We've got two boards which are almost the same size, which is actually a great thing to observe. And the communication between these two boards has to be done by wires. So of course you can have this board and underneath another board and wires dangling through between the boards in the free space, but I don't like this. This isn't a nice thing to do. So I'll be building bridges. In order to build the bridges, I will need, again, parts of the same material. So bridges will look like this. This is one board, you have the bridge, and then you have another board, you fix it there. So, we cut out some small and narrow stripes out of this board in order to serve as our bridge. Let's see if we can do that. Again, we have to cut some grooves, and in order to cut some grooves, well, let me move the camera again a bit so that we can see the groove cutting process. Right. I take the calipers itself to perform as my guide when I cut the grooves. Move away. So, the distance between two hole in this perforated board is 2.52 millimeters. So if we take two of those holes, then the distance is about 5 millimeters. That is a nice, almost round number. So I'll be taking two holes, two lines of holes as the standard width of the bridge. The third row of the holes is where my groove goes through. So hold it carefully. What happened with my hand? Why is it shaking so much? Right there. And the bigger knife goes through, cutting a hole on it. Cutting a groove on it, not a hole. There, we've got this. Right, we've got this. Now we'll need to break this open. In order to break this open, I will need some other devices. Let me see where they are. There it is. I'll need this. So, now I hold this carefully and try to pop it out. No, it didn't quite work out. It didn't quite work out. How sad. It didn't quite work out. So, that didn't work. Right, we have to think about something else. What can we do? Okay, we'll make a deeper groove so that the material tends to break along the groove, and we'll make a wider groove. So this time I take not 2, but 4. 1, 2, 3, 4. And number 5. Row number 5 is where my groove will go through. Okay, this is not a good one. I'll take a sky. Oh, come on. I'll take this box. This is better. So, I fix this on groove number 1, 2, 3, 4, 5 and pull my knife through really, really deeply. We have a groove now, once again. A groove now, once again, right there. Right, so we have got our groove. This is again not very clean, but I'll try if I can break through this. I cannot even hold, so I take it and try again. Voila! It worked. So this will be my bridge between the two boards. Now obviously, if you're noticing this meticulously, you will notice there is one problem. I have specified the width of the bridge, but not the height of the bridge, in other words, not the separation between the two boards. Now this is something which I cannot do right now, nevertheless I will fix the bridge in between and see what comes out of that. So, well, let's see, how big is this? This is about 70.65 millimeter. 70.65 millimeters. If I split it in two, then it is 35.32 millimeters. Well, 35.325 millimeters, which means I can have one board at the very bottom, one board in between at a distance of 35.25 millimeters, and another board at the very top. I like that proposal. So now the question arises, how do I fix this bridge on the board? Well, we take the almighty super glue. We take a piece of paper, we clean the side that we want to glue, we clean the part of the board that we want to glue this onto, we take the glue and I put the glue on this, not on the board, because the board has a lot of holes, so the glue will eventually go through the holes and fall on the table, which I don't want. So, oh my goodness, there's some more problems on this, but never mind, that's not that so precisely done. Eventually I will have a better option. Actually I do, I have an electronic cutter, but I will use that later. When this proof of concept satellite has been constructed, I'll be making a proper one. Yeah, well, I'll make some more money for that, but I guess I will have some money at that time as well. So, we've got the glue, and now we have to hold it on this so that it can be fixed. So, to notice it carefully, there's a little valley going down, so this is not smooth. The glue will not hold. We need to find a smoother part. Right, it is smooth, and I'm holding it there. There we go. Put it on the table and hold it steady for a while. Voila! It fixed. I'll take again the super glue and put a little bit on that. I'll take a little bit of super glue on top of... Oh shit. Right, I'll take a little bit on the top of the knife and paint it slowly, as if I was painting a Renaissance masterpiece. And the very bottom of the bridge mounted on the card. Right. Done. Now I have to remove the paint from the glue from my finger, which is gonna be a tad problematic. So, got it. So, glue removed from finger on the paper. That calls for a drink, doesn't it? Cheers. Right. Now I will leave it overnight and the bridge will be fixed, and then I will have the option of fixing two of these boards, one halfway and one on the very top. Then I have a stack consisting of 3 cards, and this will serve as a bus. I'll be using this as not as a data bus, but as an addressing bus. So the bottom circuit board will be carrying the main controllers. The main controllers will not do any intensive computation, but they will just trigger the other boards or other peripheral devices. And in order to trigger it properly, or to read something out of them, to poll them, so to say, you will have to address them properly. And the addressing has to be done in a unique manner, in the sense that everyone gets their unique address, and if you at the last moment want to stick in some other peripherals, then those peripherals should also automatically get their addresses. All this address transformation transfers, all this interrupts, all these pulling knocks on this, all these trigger signals will be carried by wires, and those wires will be mounted on this now, on this bridge. Now this is slightly problematic because when one wire is carrying a signal, then this will create a little bit of interference, a little bit of induced signal on the nearby wires. So you will have to add some filters or use some algorithm which can differentiate between the proper knock, the proper interrupt signal, and the induced signals. Generally, the induced signals are really low in power, so you can just use a system to consider the power, and the low power calls will be ignored. So you can just use a resistor to cut off the low power triggers. But we'll have to think about that. I'll be thinking about that, and I'll be putting the electronic parts together. No, yes, the electronic parts together in the third part of the video. In the second part of the video, I will be showing how to construct the complete structural of the satellite, let's say. Let's put it in this way. Well, so until next time.